For millennia, humanity gazed at the night sky and wondered, were there other worlds out there? Planets orbiting distant stars, perhaps harboring life as we know it? Today, we stand at the precipice of answering those age-old questions. We live in an era of incredible discovery, an age where we can confidently say that exoplanets, planets beyond our solar system, are not just a figment of science fiction but a breathtaking reality. Exoplanets are planets that orbit stars outside of our solar system. They come in all shapes and sizes, from gas giants larger than Jupiter to rocky worlds like our own. Some are scorching hot, while others are frigid and icy. This diversity is what makes the search for exoplanets so tantalizing. It offers a glimpse into the vast possibilities of planetary formation and the potential for life beyond Earth. The discovery of these distant worlds has revolutionized our understanding of the universe. It has shown us that our solar system is not unique and that planetary systems are likely a common occurrence throughout the cosmos. This realization has fueled our curiosity and driven us to develop increasingly sophisticated methods for finding and characterizing these alien worlds. The first confirmed detection of an exoplanet orbiting a main sequence star like our Sun came in 1995. This groundbreaking discovery sent ripples through the scientific community and ignited a passion for exoplanet hunting that continues to this day. The planet 51 Pegasi b challenged our assumptions about planetary systems. 51 Pegasi b is a gas giant, similar in mass to Jupiter, but it orbits incredibly close to its star. This close proximity results in an orbital period of just 4 days, a stark contrast to Jupiter's 12-year orbit around our Sun. This discovery forced astronomers to rethink their models of planetary formation. It demonstrated that planets could exist in environments vastly different from our own. The discovery of 51 Pegasi b was just the beginning. Since then, the number of known exoplanets has skyrocketed. We have discovered thousands of these distant worlds, each with its own unique characteristics. Exoplanets are a diverse bunch. They exhibit a stunning array of sizes, compositions, and orbital configurations. Some are gas giants, much like Jupiter and Saturn in our solar system, but often significantly larger. These behemoths can dwarf our own gas giants, with atmospheres composed primarily of hydrogen and helium. Other exoplanets are rocky, like Earth, Venus, and Mars. These rocky worlds are particularly intriguing because they hold the potential for harboring liquid water, a key ingredient for life as we know it. Some of these rocky exoplanets are even located within the habitable zone of their star. The habitable zone is the region around a star where temperatures are just right for liquid water to exist on the surface of a planet. But the diversity doesn't stop there. We've also discovered exoplanets that don't fit neatly into either category. These include super-Earths, planets larger than Earth but smaller than Neptune, and mini-Neptunes, gas planets smaller than Neptune but larger than Earth. This incredible variety underscores the vastness and complexity of planetary formation. Section 4. Seeking Shadows and Wobbles, Methods of Detection. Discovering a tiny, faint planet light years away against the blinding glare of its host star is no easy feat. It's like trying to spot a firefly next to a spotlight from miles away. But astronomers have risen to the challenge, developing ingenious methods to detect these elusive worlds. One of the most successful methods is the transit method. This technique relies on observing the slight dimming of a star's light as a planet passes in front of it from our perspective. Imagine a fly buzzing in front of a car headlight. The transit method is sensitive enough to detect that minuscule dip in brightness. Another powerful technique is the radial velocity method, also known as the Doppler spectroscopy method. This method detects the subtle wobble of a star caused by the gravitational pull of an orbiting planet. It's like trying to detect the slight sway of a person standing on a trampoline as someone else bounces nearby. A third method, called microlensing, takes advantage of the way gravity bends light. When a star with a planet passes in front of a more distant star, the gravity of the foreground star acts like a lens, magnifying the light from the background star. If a planet is present, it will cause a brief but detectable spike in the magnified light. Section 5. A new era of discovery, the future of exoplanet exploration. The future of exoplanet exploration is brighter than ever. New telescopes and technologies are constantly being developed, promising to revolutionize our understanding of these distant worlds. The James Webb Space Telescope, launched in 2021, is already providing us with unprecedented views of the cosmos, including detailed observations of exoplanet atmospheres. These advancements will allow us to study exoplanets in greater detail than ever before. We'll be able to analyze their atmospheres for signs of life, determine their surface temperatures, and even map their continents and oceans. The data collected by these missions will help us to piece together the story of planet formation and to understand the conditions necessary for life to arise. But the search for life beyond Earth is not just about finding another planet like ours. It's about expanding our understanding of life itself. By studying the diversity of exoplanets and their environments, we can gain a deeper appreciation for the preciousness and fragility of life on our own planet.